In this video, we will talk about how to use L'Hopital's rule for other indeterminate forms. So I want to begin by looking at an example. So let's suppose I have the limit as x approaches 0 from the right of x times e to the 1 over x minus 1. So my first step for a limit problem like this is always we want to try to plug in our value. So plugging in just 0 into this, we get 0 out in front. So there's no issue with just plugging a 0 in there. And then we get e to the 1 over. And here I can't just write 0 because it'll make that fraction undefined. So now I'm going to write 0 with the little plus sign. And then minus 1. So overall I got 0. And then times e to the, and I know 1 over 0 with a little plus sign is infinity. Okay, and then minus 1. So this equals 0 times, and e to the infinity is infinity. Infinity minus 1 is still infinity. This is 0 times infinity. So when we see this, when we see the 0 and then times this infinity, the 0 doesn't mean it's exactly equal to 0. It just means it's close to 0. Because because we're taking a limit, x is not allowed to be equal to 0. It's just close to 0. That's why this number at the front is close to 0. It's not exactly 0. For the same sort of reason, when we see this infinity here, that's just a symbol, which means this is really big. This number is just getting really, really big the closer x gets to 0 from the right. So typically, when you multiply by a number that's really close to 0, it makes the whole thing really close to 0. But on the flip side, when you multiply by something really big, that makes the whole thing really big. So it is unclear which of these two sort of influences, one part getting close to 0, the other part getting really big, dominates. So as a result, it's indeterminate. That is the conceptual reason why 0 times infinity is an indeterminate form. Because there's a matter of, is the 0 term something that's getting basically the question is this first part getting close to 0 faster than the other part is getting really, really big? Alright, so how can we evaluate something like this? So let's talk about strategy. What our strategy for dealing with a 0 times infinity limit will be. There's a way that we can simplify this so that we can use L'Hopital's rule on it. Okay, so what we have to do is we will bring one term to the denominator and reciprocal it. And after we do that, check if you can use L'Hopital's rule now. Okay, so what does that mean exactly? So if I look at this limit, there's sort of two factors here. There's the x, that's one of the factors that's multiplying the e to the 1 over x minus 1. That's the other factor. So I have to look at those factors, and I'm going to bring one of them to the denominator. And the easier one to bring to the denominator is x. That one's easier to reciprocal. Alright, so that'll leave me with e to the 1 over x minus 1. And then when I bring the x to the denominator, I have to reciprocal it. So I'll get 1 over x. And whoops, I forgot to write my limit. Let's not forget that. So this equals the limit as x approaches 0 from the right. So all I've done is I've just rewritten this. Alright, so now let's try plugging in. So let's try plugging into this. When we do that, the numerator is going to be e to the infinity minus 1. The denominator is going to be 1 over 0 with a little plus sign. And that's infinity. So the top is infinity, and the bottom is infinity. And this is a form I can now use L'Hopital's on. So now let's use L'Hopital's. That's why we wanted to do the step where we brought one of these terms to the denominator and reciprocaled it. It'll turn my 0 times infinity into a fractional thing that I can use L'Hopital's on here. All right, so let's use L'Hopital's. All right, so we get the limit as x approaches 0 from the right, and now I'm going to use L'Hopital's. So I'll write LH. To take the derivative of e to the 1 over x, I need chain rule. I'll get e to the stuff, and then multiply that by the derivative of the stuff. To take the derivative of 1 over x, it's helpful to write it as x to the negative 1. Okay, and then the derivative of this minus 1 is 0. And then all over the derivative of the bottom. So I'm going to take the derivative of the bottom, and the bottom is x to the negative 1. It's better to write it in that form. Now I can just use power rule to take that derivative. All right, so let's do these derivatives. We get the limit as x approaches 0 from the right of e to the 1 over x times the derivative of x to the negative 1 is going to be negative, comes in front, x to the negative 2 after I do the power rule. Same thing on the bottom, because I have the exact same derivative of x to the negative 1. I'll get negative x to the negative 2. But now that's really nice because I have cancellation. These two terms just cancel. And after we cancel them, we end up with the limit as x approaches 0 from the right of e to the 1 over x. And plugging into this now, we will get e to the 1 over 0 with a little plus sign is infinity. That is getting really, really big. And e to the infinity is infinity. And that is my answer here. So the answer to this limit, this original limit, ended up being infinity. So 0 times infinity, we mentioned, was one of our indeterminate forms. Indeterminate forms can be anything. We have to evaluate the limit to figure out for sure. We have to do more work to figure out what they actually are. So in this problem, this 0 times infinity form ended up being infinity. But in other problems, it might be 0. It might be a different number that's not 0, not infinity. All right, so I want to end this video now with just kind of summarizing, based off of the type of indeterminate form I have, what my strategy would be. Okay, in terms of how we'd approach it with L'Hopital's in mind. So if I have 0 over 0 when I plug into my limit, if this is the type of indeterminate form I get, we are good to just try using L'Hopital's. And same thing if we have a limit of the form plus or minus infinity divided by plus or minus infinity, we can try using L'Hopital's. And I say try because L'Hopital's doesn't always work. There are situations when you have a limit of the form 0 over 0 or plus or minus infinity over plus or minus infinity, but doing L'Hopital's on it just for some reason isn't helpful. And we'll see one of those on our homework, just to show you that it can happen. All right, so we've talked in this video about 0 times infinity forms. If we have something like that, our strategy is going to be to bring one term to the denominator and reciprocal it, then see if L'Hopital's applies. So I still need to, after I do that, plug in and see if I have one of these forms I can do L'Hopital's on. But if I do, then use L'Hopital's. If we have an infinity minus infinity limit, our strategy will be, we will need to get a common denominator first. Get a common denominator. And then after that, then see if L'Hopital's applies. Then see if LH applies. Okay, and then there are a few other indeterminate forms. So 1 to the infinity is an indeterminate form, 0 to 0, and infinity to 0. And we haven't really seen these in our class. These are indeterminate forms you would see more in a STEM calculus class, so not one like ours. I'm focusing less on these indeterminate forms and more on the first 4. Okay, but let me just give an example. So for example, the limit as x approaches infinity of 1 plus 1 over x to the x power. If we plug in infinity into this, this ends up being something of the form 1 to the infinity. And when I say 1 here, it's not exactly 1. It's a little bit bigger than 1, because you're doing 1 plus a really, really small number here in the parentheses. It's a little bit bigger than 1 technically. And the exponent is getting huge. And this is an indeterminate form. It turns out what this equals is actually e, which is a bit bizarre. It's a bit bizarre that this limit here, which doesn't seem to have any trace of e in it, ends up equaling e. So there's a lot of interesting stuff that can happen like that with these other indeterminate forms that are in this sort of exponential form. So for these other ones, we personally won't cover these. These appear more in STEM calculus classes. So the main reason why we're not talking about them is it's a time limitation thing. I want to spend more time talking about applications. So there's just not enough time to really do these other types of indeterminate forms justice here. Let me just briefly mention why something of the form 1 to the infinity would be an indeterminate form. So I mentioned that with this 1 here, this isn't exactly equal to 1, it's just close to 1. It's close to 1, but a little bigger. But a little bigger. It was 1 plus a tiny positive number. The 1 over x is a really tiny positive number. And then the exponent is just something that's really big. So in general, if you had that number, if it was exactly 1, and you were raising 1 to a power, like 1 to the 10, or 1 to a million, that's just 1. So having the 1 at the base makes me think that, like, oh yeah, it should be 1. But having infinity in the exponent, and having the base be something that's bigger than 1, makes me think that the whole thing should be really, really big. Like in general, if you have an infinity in the exponent, and this base is something like 2, or something like 5, something bigger than 1, the whole thing is going to be really big. So it is unclear which of these forces, either this exponent getting really big, or the base getting really close to 1, which dominates. So it's indeterminate. And there's a similar justification for every single indeterminate form, so including these other ones that I've listed here, 0 to the 0, and infinity to the 0 in this row. Alrighty, in terms of our goals for the section now, we've talked about our final learning goal, which is how do we convert other indeterminate forms, like 0 times infinity, or infinity minus infinity, into a form that we can actually use L'Hopital's rule on.